You are standing inside a cylinder of aluminum and steel that is about to experience a temperature swing of more than 300 degrees Fahrenheit in the span of a few minutes. In roughly 70 seconds, a piece of the sun shield will tear away, and the space station that took nearly 5 years and $1 billion to build will begin to cook itself alive. I'm Jacob, and what you're about to hear is how the most expensive spacecraft ever launched nearly became a tomb in orbit. Skylab began as a concept in the early 1960s, born from the Cold War desire to prove that humans could not just visit space, but live there. NASA's engineers designed the orbital workshop as a converted Saturn V upper stage, a massive cylinder roughly 85 feet long and 21 feet in diameter. Inside, 3 astronauts could work, sleep, and conduct experiments in a volume larger than 3 railroad cars connected together. The entire structure was meant to be protected from the sun's radiation and thermal extremes by a micrometeorite shield, a thin layer of material wrapped around the outside like a blanket. This was not paranoia. In 1969, the Mariner 6 and 7 probes had detected micrometeorites in Earth orbit, tiny fragments of rock and metal moving at speeds that could punch holes through spacecraft. The Skylab micrometeorite shield was made of mylar, a polyester film with an aluminum backing, and it was held in place by nothing more than mechanical brackets and the pressure of deployment. No one questioned whether it would work. The design had been tested in laboratories. The physics seemed sound. The engineers at NASA's Marshall Space Flight Center, led by Wernher von Braun and his team, had created something they believed was robust enough for a year-long mission in orbit, with the possibility of extension to 5 years. On the morning of May 14, 1973, Skylab sat atop a Saturn V rocket at Launch Complex 39 at Kennedy Space Center. The weather was clear. The countdown proceeded without anomaly. At 9:37 in the morning, the engines ignited. 58 seconds into flight, traveling at a speed of around 2,000 miles per hour, Skylab passed through a region of the atmosphere where aerodynamic forces reached their maximum intensity. This is a window of tremendous violence. The air becomes nearly as dense as it will be at sea level, and the dynamic pressure pushing against the spacecraft climbs to around 900 pounds per square foot. Somewhere in those seconds, the micrometeorite shield began to peel away from the workshop. Some of the engineers later hypothesized that the shield had been improperly secured during assembly. Others believed that the aerodynamic buffeting during ascent had worked the brackets loose. The shield was never designed to withstand the full force of launch. It was meant to be jettisoned anyway once Skylab reached orbit, after the thermal environment of space had replaced the extreme heating of launch. But it did not survive that long. By the time the vehicle reached maximum dynamic pressure, roughly 105 seconds into flight, pieces of the shield were beginning to separate. No one in mission control noticed. The flight was proceeding nominally. The first stage separated. The second stage ignited. The vehicle continued its arc toward orbit. But as the spacecraft climbed and the atmosphere grew thinner and thinner, the torn shield continued to hang from whatever bracket still held it, fluttering in the upper reaches of the mesosphere like a torn sail. When Skylab finally achieved orbit, the damage had already been done. The micrometeorite shield was no longer there to protect the workshop from the sun. For the first few hours after deployment, ground controllers did not understand what had happened. Skylab's telemetry showed higher than expected temperatures in certain sections of the workshop. This was unusual, but not immediately catastrophic. The solar panels, 2 large arrays designed to fold out from the sides of the workshop once it reached orbit, had not fully deployed. This was a separate problem, but it contributed to the mystery. Controllers believed the panels were jammed. In fact, they had been damaged during the same aerodynamic event that tore the shield. One of the panels had been ripped away entirely. The other was bent at an angle, its electrical connections severed. The first crewed mission to Skylab, Skylab 2, was scheduled to launch just 10 days later, on May 25th. 3 astronauts would dock with the station. But as the hours passed and the temperature readings continued to climb, Mission Control began to grasp the true scope of the failure. Without the micrometeorite shield, Skylab was being heated directly by the sun on one side. The temperature in some sections of the workshop was reaching 130 degrees Fahrenheit. In other areas shielded from direct sunlight, the temperature was nearly freezing. The aluminum skin of the workshop was expanding and contracting. The internal equipment was being subjected to thermal stresses that no one had anticipated. Paint was beginning to bake and crack. Insulation was deteriorating. The experiment packages were heating up far beyond their design specifications. Engineers at Marshall Space Flight Center worked around the clock to develop a solution. They calculated that if the workshop continued to be exposed to unfiltered solar radiation, the temperature would eventually reach 170 degrees, high enough to damage critical systems and make the station unusable. A crewed mission was already on its way. The astronauts would arrive to find a furnace, not a laboratory. The situation demanded not just a repair, but a completely improvised solution. A protection system that had not existed 5 days earlier and would have to be designed, built, and tested in a matter of days. The engineers proposed deploying a makeshift thermal shade, a parasol made of materials that could be assembled from hardware already on the spacecraft, or that could be launched and rendezvoused with Skylab before the astronauts arrived. The idea was simple, but its execution would require a level of precision and innovation that was rarely attempted in human spaceflight. The makeshift sunshade, later called the External Thermal Shade or ETS, was designed by a team of engineers at Marshall Space Flight Center in just 4 days. It had to be light enough to launch quickly, but large enough to shadow nearly 21 feet of the workshop's diameter. The solution was elegant in its desperation. The shade would be made of white nylon cloth, aluminized on one side to reflect heat. It would be deployed through the main airlock of the Skylab workshop once the astronauts arrived in orbit, extended by a framework of poles and tethers that the astronauts would assemble during a spacewalk. The shade would not be perfect. It would not stop all the thermal heating, but it would reduce the solar input enough to bring the workshop's temperature down to survivable levels. On May 25, 1973, the Skylab 2 crew launched. Charles Pete Conrad, a veteran of the Gemini program and the moon landing. Paul Weitz, a rookie astronaut on his first flight. Joseph Kerwin, a physician and mission specialist. Their mission was no longer simply to occupy and operate Skylab. They had become rescuers. They would have to repair a broken machine in an environment that was literally hostile to their presence. The docking procedure was nominal. The hatch between the command module and the workshop was opened. The astronauts floated inside to find a hot, dimly lit interior. Equipment that should have been cool to the touch was warm. The thermal environment was stable, but only barely. 2 days later, Pete Conrad and Joe Kerwin emerged from the airlock in their spacesuits to begin what would become the most challenging and most celebrated spacewalk of the entire Skylab program. They had to deploy the makeshift sunshade from the exterior of the workshop. Wernher von Braun later called it one of the greatest acts of human problem-solving in the history of spaceflight. The astronauts worked methodically, positioning poles, attaching the nylon cloth, creating a shelter from the sun using tools that were never designed for this purpose. The work took hours. The astronauts' suits were heating up from the sunlight and from the physical exertion of working in zero gravity, but they persisted. By the end of that spacewalk, the external thermal shade was in place. Within hours, the internal temperatures of Skylab began to drop. The workshop was being saved. The experiment packages would survive. The mission could proceed. The sunshade was only a temporary measure, a band-aid on a much deeper wound, but it bought time. It allowed Skylab to operate long enough for more permanent solutions to be engineered and deployed. The workshop that nearly became a coffin in space instead became the proving ground for human innovation in the harshest environment ever inhabited by humans. But the thermal disaster was only the first crisis that Skylab would face. Just days after Skylab 2 docked, the life support systems of the workshop would present a new and more immediate threat, one that would force the crew to make dangerous modifications to equipment they did not fully understand, working in real time to keep themselves alive. That story of improvisation and survival against impossible odds is waiting for you. It begins just days after the hatch opens,